Here we go. So this is you're going to be pulling information from your brain from the pre-quiz you took the other day. Okay, so by the end of this lesson, you'll be able to describe what a Coulomb is and use Coulomb's law to calculate the net force. I will give you a hint. It is not E. It is not E. Thumbs up when you have a guess. Have a conversation. Okay, correct answer is got a D, two D's on the table. Got a couple nods. Kind of like voting, like bidding. Correct answer is D, dangerous dinosaurs. Okay, so this is a big difference between chemistry and physics. So in chemistry, you you measured charge simply by counting how many extra electrons or extra protons there were. But in physics, we're not looking at atoms or molecules. We're looking at macro-sized objects, things that you can see with your eye and hold with your hand. Okay, and there's going to be a bunch of extra electrons or protons. Okay, so to measure the charge like you measured in chemistry, that would be similar to measuring the distance from here to San Francisco in inches. It's ridiculous. It actually doesn't even communicate anything. It'd just be such a huge number. Like you need a bigger unit. You need something like, oh, maybe like a mile. Okay, that would be a more appropriate unit. So when we're trying to figure out the charge on something macro size, we need a bigger unit than just counting onesies, twosies. Okay. Here's another analogy. We count eggs by the dozen. 1 dozen, 2 dozen, 3 dozen. We don't count 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 5. 1 dozen, 2 dozen, 3 dozen. Okay. A Coulomb is just a really big egg carton for electrons. You okay with that? Okay. So, and in order to have -1 charge, you need that many more electrons than protons. Okay. Okay, neighbor. Correct answer is not D.
It's just one atom. Just one atom.
Mm-hmm. If I gave you 2 eggs, how many dozen would that be? Be 2/12, or more specifically 1/6, more correctly 1/6. It would be less than a dozen, right? It would be a fraction of a dozen. If I gave you 2 extra protons, that's going to be a fraction of a Coulomb. Actually, a really small fraction, because that container that you're filling electrons has 6.25 times 10 to the 18th slots in it, and you only filled in 2 of those slots. C. Good with that? You see, I'm trying to like make connections with what you're used to and like bring it into the physics way of thinking. Good with that? So 1 Coulomb of charge is actually pretty big. To give you an idea, a lightning bolt has somewhere around 10 coulombs of charge. Okay, to measure, to like mess with a Coulomb of charge, that'd just be dangerous. The amount of charge on our packaging peanut was somewhere in the realm of like micro coulombs. Okay, so all right, so I've got this Coke can. We're going to assume it's neutral. Okay, I'm going to charge this rod negatively. Tell me what's going on inside this can microscopically. Flirting with the edge. What's going on inside the can microscopically? Oh, that's so close. What's going on? Talk to me. Tell your neighbor. Don't tell me. Tell your neighbor. What's going on? Oh, yeah. Tell your neighbor what's going on microscopically inside the. Okay, what do you say? Yep. Electrons are running away from the negatively charged rod. So why is it rolling it towards it if the electrons are going away? Because the protons are closer. As D goes down, what happens to the force? As D goes down, the force goes up. Okay? The protons are closer to the rod than the fleeing electrons. So there is a force of attraction and a force of repulsion, but which is stronger? Attraction is stronger because the protons are closer. And so the can rolls towards the rod because the net force, the total force, is towards the rod because the force of attraction is greater. Good with that? Give that one a shot. Tell your neighbor. Tell them why you think so. Correct answer is? Correct answer is D. Dangerous dinosaurs. Okay. They're repelling each other, therefore they have to have like charges. Whether it's positive or negative, we don't know. Okay. Next question. Hint. Correct answer is C. If object A exerts a force on object B exerts an equal force back on object A in the opposite direction. Newton's third law. Same force. Always. Go to that. Okay. Oh, good question. Good question. I'll clarify that after this one. It's a great question. Have a conversation. What do you say? Got some C's, got some B's. D. Okay. Are we good with the fact that it's repelling each other? Both are positively charged. There's a reason I put that question right before this question. Newton's third law still is a thing, will always be a thing. D, dangerous dinosaurs, is the correct answer. They have the equal amount of force. What happens if, like, this gets, like, more charge? Well, then they're both going to experience the same greater force of repulsion. Or if this became more charged than that, you okay with that? They always will experience the same amount of force in the opposite direction. Good there? Okay. All right, so coming back to this scenario, we've established the fact that they have the same type of charge. Both are positive, both are negative. We're not sure which. So they have the same type of charge. But what this question, the follow-up question is, which one has more charge like the magnitude, the size, the amount of charge, the numeric value of the charge. Both are positive or both are negative, but how much charge is there? Tell your neighbor what you think. Correct answer is C. They may be the same. They may not be the same. In this case, they experience the same force, but they had different charges. They could be the same, though. I don't know. I don't know. Good with that? Okay. So you got a scenario. You have sphere A and sphere B. I want to find the electric force between those two spheres. And I'm using this equation, Coulomb's law. So a lot of times, people use D and R interchangeably. It represents the same thing. It's like the distance between. Um, so what I want you to do is pull from this information that the variable or the measurements that you care about to find the electric force. Don't actually calculate it. I just want you to filter what information is good and what information is extra. Charge. Thumbs up when you're good. Okay, that's given to you all the time. It's constant. 8.99 times 10 to the ninth. You won't have to memorize that. I'll give that to you. Okay. Q1 and Q2 are talking about the charge on both objects. Which one's Q1, which one's Q2 doesn't matter. Okay. And then D is the distance of separation between their centers. Good with that? This, that, and that. That's it. The rest is extraneous. 8.99 times 10 to the ninth. And that'll be given to you on the worksheets. Okay. All right, so let's do an example problem. So you have a packaging peanut that has a charge of negative 3 microcoulombs on it, and a clear strip has a charge of plus 15 microcoulombs, and they're 30 centimeters apart. How much electric force is acting on them? So we're going to employ Coulomb's law. The electric force, K, is 8.99 times 10 to the ninth times, I'm going to focus on D first. So D is 30 centimeters. But what do I need to do to the 30 centimeters before I plug it into this equation? Convert to meters. Right? Right? Okay. So I divide by 100. So that's 0.3 meters Now you square that. Okay. Let's pretend I had, instead of 30 centimeters, it was 30 micrometers. I'd still need to convert to meters, right? Instead of dividing by 100, I would need to divide by 1,000,000. Okay. I have the same issue with this. I've been given microcoulombs. I need to convert to coulombs, just like if I was given centimeters, I need to convert to meters. Okay, so Q1 I'm going to say is 3 times 10 to the negative 6th coulombs. This times 10 to the negative 6 takes care of, converts micro to the base unit. I just memorized it from this chart. Whoop, there. You will actually need to, just that one, and you will, just because you'll do it so often. Okay, so that takes care of the micro times 10 to the negative 6th. Also check this out. Drop the positive and negative sign for the charge. Drop the positive and negative sign for the charge. You will do that the entire time in this class. You have a charge. You are going, when doing the math and plugging stuff into your calculator, ignore the positive and negative sign. Okay? Well, that'll come into play later, but not when you're calculating the math. All right, so, and then Q2 is 15 microcoulombs times 10 to the negative 6. I recognize that that is improper scientific notation. It's fine. Your calculator can handle it. Okay, so go ahead and calculate. Remember to square the distance. Make sure you can get 4.495 on your calculator. If you didn't, you probably forgot to square the radius. Thumbs up if you're good with a 4.495. Staring you in your face on your calculator. Proof of calculator skills. I don't know. Let's see what that. But good there. Okay. What's the unit? What did we just calculate? Hey. Right there. Take as many as you like. What did we just calculate? What? What do we calculate? Hey, what do we calculate? Force. What's the unit for any type of force? Newton. Oh, crazy.
It's all coming together.
No way. It is. I know. All right. So B. Which way is the peanut being forced? Tell your neighbor. See if you can figure it out together. Which way is the peanut being forced? To the right or to the left? Correct answer is. How'd you figure out left? They're opposites, therefore they attract. So you would say attracted to the left. Both the strip and the peanut both experience that same force, 4.495. Because of Newton's third law. The peanut is just being forced to attracted to the left. If the strip was on the other side, it would be forced to the right. Do that. Questions there? Okay. So to find the net force on an object, if there's more than two objects, here's the strategy. What you're going to do, so we're trying to find the net force on object 2. What we're going to do is take it in pairs. Okay, so we're going to ignore object 3, figure out the force between 1 and 2. And then we're going to ignore object 1 and figure out the force between 2 and 3. And then we're going to find the resultant of those two forces. Thumbs up when you have a guess. Tell your neighbor and tell them how you got to that conclusion.
Oh, yeah. It's like third.
Oh, you're right though. She said it would be like a held away from one to one to so opposite to the right. I was asking net force. I think it's right.
It's right.
Correct answer is?
Give me a 0.
Okay. We're looking for the net force on 2. So between 1 and 2, what's going on? Attraction or repulsion? Repulsion. Which way is 2 being repelled? To the right. Between 1 and 2, it's being repelled. Does that make sense?
Wait, can you restate all that?
Yep. Okay. Between 1 and 2, what's going on? Attraction or repelling?
Repelling.
Repelling. Which way is 2 being repelled? To to the right.
Okay, cool.
Okay?
Just making sure.
Now, we're going to ignore 1. What's going on between 2 and 3? Attraction or repulsion? Attraction. Which way is 2 being attracted? To the right as well. So you got 2 forces to the right. The resultant of those 2 forces is to the right.
Yeah, that's basically what I was thinking.
Okay?
We're gonna go math while
Okay? But does that make sense? Everybody good with that? Okay. Same scenario, but this time we're looking at object 3. What's the net force on 3? What do you say? Did you talk to your neighbor already?
Yeah.
Okay. Okay. Correct answer is B. To the left. Okay. So between 2 and 3, there's attraction being attracted to the left. Between 1 and 3, there's attraction to the left. Okay. So net force is to the left. Now, here's a follow-up question. The force that 1 exerts on 3, if we took 2 away, just made it disappear, would that make this force greater, smaller, or the same if 2 is there versus not there? Okay. Okay. The force that 1 is exerting on 3. This is this force here. Okay. If I took 2 away, is that going to change that force? Is that force going to get stronger, weaker, or is it going to stay the same? Okay. When I was in your shoes, when I was in high school, I used to think that 2 would run some kind of interference pattern, kind of like get in the way, like box out 1, like, dude. Okay. Okay. So check this out. This tennis ball weighs something, right? Has a certain weight. There's a certain force of gravity acting on it. If I take this cart and I put it between the ball and the earth, like, I just changed its weight. Look, I'm like boxing it. I'm like separating between this and there. No, that's stupid. Okay, same thing. I stick 2 here or not, it doesn't matter. The force of attraction will not change. The individual force between 1 and 3 is not going to change. The net force will change, yes, but the individual force that 1 exerts on 3 will not be affected by sticking 2 there. Good with that? Okay. All right. I'm going to change this scenario. We're looking at the net force on object 1. I'm going to change the scenario from the question. I'm going to say, let's say they have the same amount of charge. They have equal magnitudes. Run that scenario. Net force on object 1. Have a conversation. And tell them why you think so.
Yeah, no, all of them.
And everything. Well, you got two masses going. Right. Keep going right.
Correct answer is all right. What's going on between 1 and 2? Repulsion. Which way is 1 being repelled? To the left. Everybody all right with that? And between 1 and 3, what's going on? Attraction to the 1's being attracted which way? To the right. If these have the same charge, which of these two forces are greater? Or are they the same? If they have the same amount of charge, which one's closer to 1? 2 is closer to 1. Therefore, this is stronger than this.
Yeah, it's going left.
It's gonna go left.
Yeah.
If they have the same amount of charge.
Which they do.
Because I said so.
Yeah.
Okay. Now, coming back to this question, Mitchell.
On a test, would it say that they have the same amount of charge, or would it say that their magnitudes aren't stated? Because wouldn't that make it cannot be determined?
Okay, so hang on to that thought. So let's come back to this original question. Okay. Is it possible that charge 3 could be big enough to make this force greater than that force? Is that possible? Yes. Is it possible this charge is big enough to make this bigger than that? Yeah. So if you don't know the magnitudes of the charges, it's anybody's ball game. You have no idea. Cannot be determined. That makes sense? So it's dependent upon not only the charge, but also the distance away. Good with that? Okay. The correct answer for the original question was D, cannot be determined. Curveball. All right, so let's do this like hardcore. Here's some numbers. I want to know the net electric force on object C. So the same strategy applies. Okay, we're going to take it the pair of A and C, and then we're going to take the pair B and C. We're looking for the net electric force on object C. Take it in pairs and make sure C is always one of those pairs. Okay, so between A and C, and then B and C. Okay, if you're tracking with me, see if you can beat me to the answer. Okay, between A and C, got 8.99 times 10 to the 9th times 4 times 10 to the negative 6th coulombs. Nope. 14 times 10 to the negative 6 coulombs times 7 times 10 to the negative 6 coulombs over the distance of separation squared, so 0.5 meters. Square that. 3.5 newtons. And direction-wise, which way is that? C being forced by A? To the right or to the left? To the left. So attracted to the left. So C is being pulled this way. A is being pulled this way, but I don't care. And now I'm going to do between B and C. See if you can beat me to the answer. How to do? 2.8. Get it? Okay. And between B and C, they're repelling each other. So C is being repelled to the right. Are we done? No, but we are so close. Tell your neighbor how you would find the net electric force on object C. How would you find the net electric force on object C? Notice that they're in opposite directions. So the net electric force you're going to subtract. Okay. So you got 3.5 minus 2.8 equals 0.7 newtons. Which way is it going? To the right or to the left? Great question. So the question was, which one do you subtract first? I always subtract the bigger one. And then which ones, so which way is it going to go? To the right or to the left? Which one's bigger? Left is bigger. So to the left. Okay, you could also, if that kind of rubs you the wrong way, you could say, okay, this is going in the negative direction, this is going in the positive direction. I'm going to add those two together, find the resultant force. You could do that way as well. Okay, here's the pitfall not to fall into. Attraction. Oh, that's so inclusive. Yeah, that's got to be positive. Oh, repulsion. Oh, that sounds bad. That's negative. Don't do that. Okay? Do not put positive negative signs because attraction's positive, repulsion's negative. Also, don't stick in positive negative signs into the charge. Figure out what goes on here. C is being attracted to the left by A. A is being attracted to C to the right. We just cared about C only. I didn't care about what happened to A. Okay, good with that? So you got a worksheet due tomorrow.